Hi everyone, welcome to SM Chemistry 99. Before beginning the lesson, may I suggest that being consistent is the key to success. And with that thought, let's begin Chemical Equilibrium Part 1. So let's begin with the types of reactions that we need to know for understanding this lesson. The first type is irreversible reactions, which mainly take place in one direction. That is, if A is my reactant and B is my product, they will proceed primarily in this direction from the reactant to the product side. The second type is reversible reactions, which take place in both directions. That is, from the reactant to the product and from the product to the reactant. These two processes will occur simultaneously. The process where the reactant changes to the product are known as the forward reactions, and in the case where the product is changing to the reactant is known as the backward reaction. So for a reversible reaction, the forward and the backward reaction are happening simultaneously. We also need to understand that as and when the reaction begins, the reverse process will not start immediately. After a certain period of time, the reverse process will begin. And at that point, when the reverse reactions are happening simultaneously, and when the rate of the forward and the rate of the backward reaction becomes same, we say that equilibrium has been attained by the process. We also need to remember that a reversible reaction never goes to completion. What does that mean? That the entire amount of reactant, in this case reactant A that we have or that we begin with, will never completely end up as the product B, but before all of it is consumed, the reverse process would have begun. Now let us have a graphical representation for the state of equilibrium. So on my vertical axis is the rate of reaction, and the horizontal axis represents time. So this curve of mine is representing the rate of the forward reaction, that is when the reactants are getting converted into the products. As time progresses, the amount of the reactant is consumed because it is getting converted into the product, and since the raw material for conversion of the reactant to product is going down or is becoming less, and you can see a dip in the curve for the rate of reaction for the forward reaction. And as and when the backward reaction begins, you can see its rate increases with the time, simply because the concentration of the products increase with time, and at that point, when the rate of forward reaction becomes equal to the rate of backward reaction, we say that a state of equilibrium has been attained. Now let us try to understand this a little more. So I have over here a general reaction A changing to B, but because this is representing a reversible reaction, I have these two arrows. So let me read it as A reversible B. And let us assume that a certain amount of reactant A was taken and it got converted to B, and the reverse process also began. At a certain point, I find that this is our point under study, that at a certain point in time, we find that 10 particles of A, 10 moles, whatever, let's say 10 units of A are present, and they have got converted, let's say hypothetically, to 7 units of B. At this point, let me say after this point, the 11th A that gets converted to the 8th B, it is followed by 1B changing to 1A. That means my net change is 0, because after these two processes where 1A changed to 1B and simultaneously 1B changed to 1A, the net change in my concentrations remains the same. That is 0. That is, the concentrations remains the same. A is still 10 and B is still 7. At this point, the concentrations of A and B have become constant. They don't have to be equal. They are constant, simply for the reason that the rate of forward reaction is the same as the rate of backward reaction. Hence, the net change is 0, and we say a state of equilibrium has been attained by our process. Now, just to understand the fact that the concentrations are constant and not essentially equal, what you may observe three cases at the point of equilibrium for a given reaction. The first may be, as I have depicted, that concentration of A could be more than B, or it could be the concentration of B could be greater than A, or it could be that the concentration of A is equal to B. But whatever may be the situation for a given reaction, the concentrations do not change with time at the point of equilibrium, that is, net change is zero. And as a direct consequence of the state of equilibrium, we'll understand, let's assume that at the given point of equilibrium for our reaction mixture is a light pink. Let's say light pink would be a contribution of some color contribution by 10 particles of A and some color contribution by 7 particles of B. Since the process is happening equally in both directions and the particles at equilibrium are still remaining the same, so the color of the mixture will remain, the product and reactant mixture at equilibrium will still remain the same. That is, we come to a conclusion here that at the point of equilibrium, certain properties which are observable, which we can note, which we can see, happen to be or become constant. In this case, it was color. If you had a specific rotation, it could become constant, or concentration, as I have just said, becomes constant. Another fundamental term that we need to understand here is dynamic equilibrium. What is the meaning of dynamic? Dynamic means something in motion, movement, on the go. So, how does it fit with the term equilibrium? So, if we look at this small equilibrium status that we have just understood, we find that once the equilibrium has been attained, there is no change in the concentration of the two components in under study. But that does not mean the process is not working or is not undergoing any change. There is a change. A is still changing to B and B is still changing to A. But since the rate of the forward change or forward reaction is the same as the rate of backward reaction, thus the net change is zero, but the reaction is still occurring, and therefore, because the process is still occurring, therefore the process is known as dynamic, and we have reached a state of equilibrium in our process, and hence it is called dynamic equilibrium. Some features of chemical equilibrium. As I just discussed, observable properties will attain a constant value because our components have become constant. So any property which their amounts may decide would also attain a constant value, like we talked of concentration, we just talked of color or specific rotation or any other observable property. We can also understand that attainment of equilibrium for a reversible reaction can happen from either side. So if I began with A reversible B, my equilibrium will also be attained if I began with B changing to A. The situation is the same. Equilibrium status would be attained for either processes when the rate of forward reaction is the same as the rate of backward reaction. Equilibrium is attained in a closed container. This is an important fact. It is attained in a closed container so as to not allow the escape of any gas reactant or product which may be there, and if one of the components escapes, the backward process will not happen, or not allowing a solid to separate out. We discussed just now that equilibrium is dynamic in nature, and an important fact that the equilibrium point remains unchanged in the presence of catalyst. Like if we used a catalyst, let us talk about the function of a catalyst in this case as being able to accelerate the reaction or increase or enhance the rate of reaction. So it enhances or accelerates the rate of forward reaction and the backward reaction to the same extent, such that the value of the point of equilibrium constant is the same at whatever point it was attained. However, the equilibrium point is attained faster. Like in the previous thing we studied, that it would be attained for, if I used a catalyst here, the point of equilibrium would be here only. But instead of taking, let's say, 15 minutes, it would take a lesser span of time to attain that point of equilibrium. Next, let's come to something known as the law of mass action. Before talking about the finer points of law of mass action, let us understand basically what it is concerned with. So the law of mass action is going to help us to understand how to find the rate of reaction. So let us take a general reaction A, B, C, interacting to give us products, where the smaller letters represent the coefficients, that is, the number of moles of A is A, the number of moles of B is B, and so on. So the rate of reaction is proportional to the product of the concentration of the reactants with each concentration term raised to the coefficient, the stoichiometric coefficient that is appearing in the balanced equation. Here I want to use the term active mass. So Goldberg and Vach, the statement they have given, instead of using the words molar concentration, they use the word active mass. Now what is active mass? Out of the given initial concentration, all of the reactant is not getting converted into product. That much amount which is actually active in terms of interacting and forming the product is known as active and mass. But for all practical purposes, we are using the words active mass in the law as a statement, but otherwise we will equate the term active mass to molar concentration. Now if you need a solution, we need to eliminate this proportionality and we introduce a constant known as rate constant. So the rate becomes equal to the constant K and the product of the concentration of the products, or the active masses of the reactants, with each active mass term raised to the stoichiometric coefficient that is present in the balanced chemical reaction for a given process. The constant K over here is known as the rate constant. From here we move on to law of chemical equilibrium. What does this law say? So again we take a general reaction. Now because we are talking of equilibrium, we show the reversible process like with these arrows. So again I begin with a general reaction. A gives B, reversible C, D, where these two are reactants and these two are products. Then at equilibrium, the ratio of the concentration of products to that of reactants becomes a constant that we have just studied, that at equilibrium the concentrations become constants and so the ratio will also be constant, and that constant ratio of the product concentrations to that of the reactant concentrations is known as the equilibrium constant, represented with a capital K. And this entire expression which is in the box is known as the expression for the law of chemical equilibrium, or they are also known as equilibrium constant expressions. So what is equilibrium constant expression? It's simply the ratio wherein the numerator we have the product of the concentrations of the products. Here we have in the denominator we have the product of the concentrations of the reactants, and with each concentration term raised to the stoichiometric coefficient which is featuring in the balanced chemical reaction. And just so that you know how we have derived this expression for chemical equilibrium, let's begin with a general reaction. Just a moment, let me just fix this. Yeah. So for a general reaction, I have eliminated the coefficients here just so that the comprehension becomes easier. So we have A plus B, the reactants, reversible C plus D, which the status of this equation under study is at equilibrium. So according to the law of mass action, we know that the rate of, if I'm talking of the forward reaction, rate of the forward reaction would be the rate constant into the product of the concentration of reactants. K1 I represent as the rate constant for the forward reaction. Rate of backward reaction would be the rate constant into the product of the concentration of the products, where K2 is the rate constant for the backward reaction. We already have discussed that at equilibrium, the rate of forward reaction will be equal to the rate of backward reaction. I already have expressions representing the same. I just place them, rate of forward and rate of backward. Now I want to get the ratio of product to reactant, so I have K1 upon K2. I get this upon this. And so K1 upon K2, this ratio is a constant which I equate to a new constant called K, capital K, which we just talked of, which is equilibrium constant, and equal to the product of concentrations of the products, sorry for that, and upon concentration of the products of the reactants. So how would we define equilibrium constant? Exactly the same as we just said, that it is the ratio of the product of the concentration of the products with each concentration term here also raised to the stoichiometric coefficient that would be appearing in its balanced form upon the product of the concentration of the reactants, again each concentration term being raised to the power which is appearing as the balancing coefficient in its balanced equation. Now, this equilibrium constant K may be read or studied in two modes. One, in terms of molar concentrations. That means when we are expressing the concentration of the reactants or products in terms of moles per liter, then we are saying in terms of molar concentration. Then this ratio, that is the equilibrium constant K, is written as K, or may also be written as Kc. So if Kc is not there and only K is written, you must understand that we are representing the concentration in moles per liter or molar concentration. If I have gases in my reaction, then I may also represent the active mass. Active mass is what? That much amount which is active during the course of the reaction in terms of partial pressure. Then my ratio, that is the equilibrium constant, is known as Kp. The subscript C represents what? That the equilibrium constant is being read in terms of molar concentration, and the subscript P to the equilibrium constant represents that the concentration or the active mass, let's say, is being represented for in terms of partial pressure. Now let us understand, we talked of Kp, that is the equilibrium constant, being read in terms of partial pressure. So let's have a small illustration to represent the same. So again I have the same general reaction AA, BB, reversible C, D, but I have also shown the physical state of each component in the reaction as a gas. And this status is again equilibrium because I am talking of the equilibrium constant. So let the partial pressures of A, B, C, D be represented as PA, PB, PC, PD. Then Kp, equilibrium constant, whether in terms of concentration, moles per liter, or in terms of partial pressure, will be the product of the reactant concentration, will be the product of the concentrations of products to that of reactants. It will always be the same. But because it is pressure here, it will be the product of the partial pressures of the products to that of the product of the partial pressures of the reactants, with each partial pressure term raised to the stoichiometric coefficient which is featuring in the balanced chemical reaction. So what is Kp? Kp is partial pressure of C to the power C into partial pressure of D to the power D upon partial pressure of A to the power A into partial pressure of B to the power B. And in case this was Kc, then what would it be? Kc is equal to concentration of C to the power C, concentration of D to the power D upon concentration of A to the power A into concentration of B to the power B. May I remind you that the square bracket, if I enclose anything in a square bracket, it indicates the molar concentration of that entity. And just to recap, let us write an expression for Kp for this reaction. N2 3H2 reversible 2NH3, where all the components in the reaction are gases. Then Kp, K is the equilibrium constant, P indicates that we are representing the active masses in terms of their partial pressures. Product partial pressure, that is partial pressure of NH3 to the power 2 upon partial pressure of N2, no power, so nothing here, into partial pressure of H2 to the power 3. So each partial pressure term has to be raised to the stoichiometric coefficient which is present in the balanced reaction. Now another very important term that we are going to do is concentration quotient Q. As the term suggests, concentration quotient. Quotient means we are dividing and getting an answer Q, quotient, and it's in terms of concentration. So let's begin with the same general reaction. AA plus BB reversible CC plus DD. My concentration quotient would be Q, would be the answer to my division, which is the quotient. Division of what? Product concentrations upon reactant concentrations. Do not forget that each concentration term has to be raised to the stoichiometric coefficient which is appearing in the balanced reaction. This is known as concentration quotient. And a very important conclusion or a fact that we'll remember here is that when the reaction is at equilibrium, the concentration quotient has a different name or a special name, and that name is K, which we just studied. K is the equilibrium constant. So Q and K, they are the same. Quotients of two concentrations, product concentrations divided by reactant concentrations. But at any given point during the course of the reaction, if I divide the product concentrations by the reactant concentrations, my answer would be called Q, concentration quotient. However, when I have reached the state of equilibrium and the same division is carried out at the point of equilibrium for product and reactant concentrations, then my concentration quotient has a special representation, and it is known as the equilibrium constant K. And when the active masses, this I just told you that the square bracket represents molar concentration. When the active masses are being represented in partial pressure terms, then Kp instead of K or Kc, it would be called Kp, partial pressure of C into partial pressure of D, partial pressure of A into partial pressure of B, with each partial pressure term being raised to the stoichiometric coefficient featuring in the reaction. And if the reaction is in a state of equilibrium, then Qp, the subscript P is for the term in the mode in which the concentration is or the active mass is being represented, is known as Kp. So from here, from these 2 points, we need to remember that Q is the concentration quotient at any point during the course of the reaction. However, at the point of equilibrium, Q becomes equal to K. If I read my concentrations or active masses in terms of moles per liter, it's known as K or Kc. And if we read our active masses in terms of partial pressure, then our equilibrium constant takes the subscript P, that is equilibrium constant in terms of partial pressure. Now, as a follow-up to equilibrium constant, this is something what we call application of information. The information we've received so far, how do we apply that to understanding the concept in question? So predicting the status of the reaction on the basis of the mathematical value of Q or the concentration quotient. We just understood what is Q. What is Q? Q is the ratio of product concentrations to reactant concentrations at any point during the course of the reaction. This is in continuity, that when Q, mathematically Q happens to have the same value as the equilibrium constant or is equal to the equilibrium constant value, it is obviously understood that process is at equilibrium. So how do you ascertain that the state of equilibrium has been attained by our system or our reaction? When the mathematical value of Q is the same as that for equilibrium constant, we say that the system has attained equilibrium. Second case, when Q, that is concentration quotient, is less than K, then whether it is Q, just a moment, whether it is Q or it is K, for both of them the story is that product concentration upon reactant concentration. So if Q is less than K, Q is less than the arithmetic value of K, then Q always wants to, please remember, all systems want to return to a state of equilibrium or want to be at a state of equilibrium. So if Q is less than K, what does K define? K defines the state of equilibrium. If Q is less than K, Q wants to move towards K, and because this is Q by 1, K by 1, this wants to increase its value, it will increase its value if P is increased, and P will increase if more product is formed, and more product will be formed if the reaction tends to proceed in the forward direction to a greater extent. So you need to understand that at this point we are not at equilibrium. We are trying to move towards equilibrium by increasing the value of product, and that will happen if my reaction moves to a greater extent towards product formation, that is towards the in the forward reaction. The third case would be when Q is greater than K. That means how would Q be? Q or K is equal to product conc upon reactant conc. Q has surpassed, it has crossed the equilibrium point. When that happens in the next class, because it won't happen automatically, but we'll see how that happens. But at this point, just mathematical implications of the relative values of Q and K. If Q, what is Q? At any point during the reaction when product conc is divided by reactant conc, the ratio is known as Q. So if the mathematical value of Q has become greater than K, we just understood that all systems want to return to K. So if it has become more, that means the numerator should be decreased. What is the numerator? The product. So the concentration of product should become less, and the concentration of product will become less if the product is consumed. And how will the product be consumed during the reaction? When the forward reaction is happening to a greater extent than the backward direction. So here you will make a conclusion that this Q has become greater than K. That means the equilibrium was already attained and has crossed the equilibrium point. System will try to regain the equilibrium by decreasing the value of Q so as to become equal to K. That will happen when P becomes less. P will become less when it is consumed. And how will it be consumed? When the product will be converted into the reactant. That means backward reaction will happen to a greater extent. So this is one application of knowing the values of K or the concentration quotient. Another aspect is one more application of the value of K, that is in predicting the direction of reaction we have just done, whether the rate of forward is equal to the rate of backward reaction, whether the reaction is moving in the forward direction to a greater extent, or under this situation the reaction is moving to a greater direction to a greater extent in the backward direction. Another aspect of understanding the value of K is predicting the extent to which the reaction has occurred. Now what does this mean? This means that we've already said that once a process begins in the forward direction, at a certain point during the course of the reaction, the reverse will begin. And then at a certain point during the course of the reaction, equilibrium status would be attained. So extent of reaction implies that at the point when equilibrium was attained, how much was the extent, or how much was the extent of the reaction in the forward direction as and when or before it attained equilibrium. So if I have a mathematical generalization is there, if Kc is greater, K or Kc is greater than 10 power 3, the reaction is about to reach completion, means almost most of your reactant has been converted into the product, and now the reaction has attained equilibrium. That is the meaning of it has attained completion. The reaction is about to attain completion. Completion means how much reactant you had, almost all of it has got converted into products, and at that point the equilibrium status was attained. If Kc is less than a power minus 3 of 10, then the reaction is about to start or has hardly begun or is taking place to a greater extent in the backward direction rather than in the forward direction. And if Kc value is in between 10 power minus 3 or 1 minute 10 power minus 3 to 10 power 3, then reaction is in between, that is equilibrium has been attained, and an appreciable concentration or it is about to, it is in between the equilibrium point and about to attain equilibrium, and you have appreciable concentrations of the reactant as well as product as and when equilibrium is present. So this we'll do once more. Predicting the extent of reaction, what does that imply? That before the point of equilibrium has been attained, what was the extent of reaction that occurred in the forward direction. So if Kc is like around a little more, is more than 10 power 3, then reaction is about to reach completion. What does that mean? That most of the reactant got converted into the product, and then your point of K or equilibrium constant or equilibrium point was attained. If your Kc is at 10 power minus 3, that means the reaction had hardly progressed before what has happened, the point of equilibrium has attained, and Kc is lying in between these two terms, that is between 10 to power minus 3 and 10 to power 3, that is reaction is somewhere in between, and appreciable amounts of reactant and product would be present at equilibrium. Over here is reached completion, that means less of reactants would be there, more of products would be there. If Kc is 10 power minus 3, more of reactants would be there, less of products would be there. And if Kc is in between the two values, we have appreciable amounts of both the reactant and the product. And with that, we end this lesson for part 1. And do remember to repeat, revise, and reinforce. And with that, for such like videos, if you enjoyed the class, please like, share, and subscribe my video. Thank you.